Okay, the power question. Every year they ask a question on power. And you really don't need much more theory here other than the power equation, which I'll go through in a second. But they ask this every single year. Every single year. I've gone back to 2017 and it's asked every single year. And you have every single one of the times they have asked it on power here in this worksheet. It's like 32 questions here. I answered all the questions from 2020 to 2022, and then I extracted the answers for the earlier years. But this one's actually not too difficult if you've understood the energy, work energy, and the forces that I've done. The only additional concept that we need to understand here is power. So make sure that you've watched, and I'll put links in the description, but you should have watched the whole series. Remember, it's in order. So I'm developing through, we're progressing through chronologically here. But the work energy question, the question on connected particles, and inclined slope forces question. Those three are pretty fundamental for this. Anyway, so what is power? Power is simply this. Power is literally the rate of doing work. And so you can derive it from work done. If you have a force that's doing work on an object and moving it at displacement s, from that, by just substituting in s equals vt, the distance equals velocity times the time, we get the power equation, because the work done divided by the time is simply power. And so that's it. So power equals force, the driving force, so an engine or if someone's on a bike or something, they have an internal power which they're producing to produce a driving force to move that object at a speed v. And so the power is then equal to the magnitude of that force times v, and obviously v and f have to be acting in the same direction, but they always will be. Cool, so that's it. So make sure you download that. It's a really good worksheet. It's 52 pages long, so you've got plenty of examples there. But all we're going to do is go through some questions, give you a feel here. Like I said, you don't really need any extra theory here, but you should watch those videos that I mentioned. Okay. A car of mass 1600 kgs is pulling a caravan 800 kgs. The car and the caravan are connected by a light. So by the resistance, it's 400 for the car and 250 for the caravan. The car and caravan are traveling. Okay, so let's draw this out. So we got. Remember, you can just use boxes for everything here, because we love actually, I'm not going to say that. Boxes are perfect for everything. That's me. Okay, so we got, this is our car. Let's call this, so let's call M1. I'm just going to define these things. M1 is the mass of the car, which is 1600 kgs. M2 is the mass of the caravan, which is pulling, which is 800 kilograms. And we have the resistance on the car is 400 newtons. Resistance on the caravan was 250 newtons. So, we have a resistance on this R1. Resistance on this is R2. We will have obviously the tension in this tow bar, which will be both acting inwards. And then we'll have a driving force, which is pushing this thing forward at constant speed. FD, which we don't know. Okay, A. So I've written down what I know. I've visualized the situation. Now we can proceed to the questions. The car and the caravan, given that the car and the caravan have a constant speed of v. So this whole system overall is traveling at v. V is 25 meters per second. Find the power of the car's engine. Okay, well, so this thing is producing a force, a driving force. And so what is the power producing this driving force, moving this whole system at speed v? Well, power equals to velocity, force, the driving force times the velocity. Well, we don't know what the driving force is. We know what the velocity is, so we need to find what the driving force is. And what is the driving force? Well, the driving force, because this thing is traveling at a constant speed, the sum of the forces of the system will just equal to 0. Right? You can use Newton's second law. Sum of the forces for this whole system. All right, we'd say that equals to the mass total of the system times the acceleration of the system, but because the system is moving at a constant speed, it's not accelerating at all. So this is going to be 0, so this will all equal to 0. So therefore we get driving force. So what are the forces? We've got the driving force minus resistance 1 and resistance 2 acting in the opposite direction. Then we also have these tensions, but they're just going to cancel out. We have one tension acting that way, the same exact tension acting that way. So tension plus tension equals 0. Those tensions will cancel out, and we just get, therefore, FD equals 2. We take all these over. T and T will cancel. Get R1 plus R2. That equals to 400 plus 250. Now we have the driving force of the engine. This is going to equal 650 newtons. Now we have the driving force of the engine, therefore we can find the power of this engine. It's just going to be this, which is 650, multiplied by the speed of the system, which was 25. Okay. 25 times 650 is 16,250 watts. Watts. I usually like to write it in kilowatts because we usually get large numbers for power. So 16, you say 16.25 kilowatts. This means 1,000. Okay. You times this value by 1,000, you get it in watts. That's the power. II. Okay. The engine's power is now suddenly increased to 39,000 39,000 watts. Find the instantaneous acceleration of the car and caravan and find the tension in the tow bar. Okay, so the power is instantaneously. So all of a sudden, the power starts producing 39,000 kilowatts. So now the power of this thing is 39,000. This engine, watts. And so if we want to find the instantaneous acceleration, we're going to have to do the same thing as before, but resolving the forces. With this, we can, resolve it for the entire system, or do like we did with pulleys and other things, where maybe I'll do it like that. So where we resolve it around one mass and the other mass, and then find the tension and the acceleration, right? But in order to do this, we're going to need the new driving force, right? So it's moving at the same velocity because it's instantaneously changed. So all of a sudden, now it's producing 39,000 watts of power. So the driving force is going to be changing. It's going to be getting a lot bigger. So the driving force is going to be changing, but the velocity, because it's instantaneous, is going to be the same. So the new driving force, because power equals Fd times V, so therefore the driving force equals to power divided by velocity. Right. So the new driving force, which we'll need, is going to be 39,000 divided by the velocity, which was 25, right? Right, because it's instantly changing. So the internal power of the engine, which is changing from 16.25 kilowatts to 39,000 kilowatts. So in that instantaneous change, the velocity is still the same, but the force will have instantaneously changed as well. Right? You can have a massive force now acting upon it, which is going to increase its acceleration. Equals to 39,000 divided by 25 is 15. Right, I haven't even started my calculation yet for what I'm actually trying to find, but I know that I'm going to need the driving force. Okay, so find the instantaneous acceleration of the car and the caravan and find the tension in the crowbar. Well, we can just resolve, like we've done many times in all of my forces videos, resolve forces about car and caravan, so just call it van, car and van. Well, for the car, sum of the forces of the car is going to equal to the mass of the car, which we called M1. M1 times A, which we want to find. It's going to be, that driving force, just summing up these forces. Driving force minus R1 minus T. Minus R1 minus T equals to M1A. For that equation 1, sum all the forces van, this equals to M2, the mass of the van A, and this is just simply going to be T in the positive direction, so the forces around this are T minus R2. This will be therefore T minus this thing, T minus R2 equals M2A. we can say t equals to m2a plus r2. Equation 2. So we substitute equation 2 into equation 1. Just to note, you could have just done it from the entire system, from this, if you wanted, and this would now be MT. Okay, you could have done it like that. I'm just going to start from scratch here. Okay, so then if we get FD minus R1 minus this is M2A plus R2 equals M1A. Okay, we rearrange for A to get that instantaneous acceleration when this power is changed. So we get M1A plus M2A, taking this over, equals to FD minus R1 minus R2. Or we get A of M1 plus M2 equals to FD minus R1 plus R2, just making it look neat. Divide through by M1 and M2. M2, sorry. This M2. Okay, so therefore the acceleration will be, well, FD we calculated was 560. This will be plus, right? Right, because when we take this stuff over, oh no, it won't be minus. Right. Yep, it'll be minus. Sorry. Minus. So make sure you take, I'm kind of going faster here because it's easier. I need to make the videos quicker. Keep you mofos engaged, you know? But you should take more steps than I do. Anyway, what am I doing? So this minus R1, which was the resistance on the car, which was 400, plus R2, which was 250, divided by M1 plus M2. That was, M1 was 1680. 16. Okay, so we get 60 minus 4 D plus 800. 0.379. So the instantaneous acceleration is 0.379 meters per second squared. Okay, and then therefore the tension, if we substitute it into 2 here, tension will equal to mass 2 times the acceleration. The mass 2 was 800 kilograms times the acceleration 0.379 plus R2, which was the resistance on the van, which is 200. Therefore T equals 800 D is 333. 3.33. So we could round that, let's say 550. Ooh. Then we need B. The car and the caravan are now traveling up a hill at incline this to the horizontal at a constant speed V. The car's engine is working at 32.5 kilowatts. Find V. Okay, let's redraw it. So it's now moving up a hill with theta. Recheck these just in case. 0.05, I'm pretty sure it was. 0.05. This thing has a power. Engine has a power 32.5 kilowatts. And it's now the whole caravan of the car are traveling at speed V. Okay. This basically the only difference here is that we're going to have to deal with the weight as well. So we got to remember these things. This is R1, 2, right? They're constant. There's no change in this resistance. It says here, you know, We have a constant resistance to the motion of the car variant. So I don't say there's any change in the resistance, so we can assume it's the same. Then we have the weight 2 acting down. Maybe I'll call it F, so it doesn't get confused with work. The force acting down, then we have this driving force acting up, and obviously we have the tensions in the string here. Okay, and other than that, that's all the forces. And this whole thing is traveling at a velocity v, which you want to find. All right. Well, what we can say is the sum from Newton's second law, the sum of this for the whole system is going to equal 0, right? Because it's traveling at a constant velocity, so it means it's not accelerating. So the sum of all the forces of the system equals ma, but the acceleration of the system is 0, so it's 0. Right? And this thing is just going to equal Fd minus R1, R2, R1 plus R2, so minus R1 minus R2, then minus, you know, the force down the slope due to gravity from the car and the caravan, which should be just F1 sine theta plus minus F2 sine theta. Then we have minus T plus T for the tensions, but those will just cancel out. And so therefore we get Fd minus, take this over, we get R1 plus R2 plus sine theta of F1 plus F2, right? And Fd equals to, from this, Fd equals to power over the velocity. If we want this thing, it's just going to be this power which it's producing divided by the velocity it's moving at, which we want. So this thing here will be P over V, which equals to R1 plus R2 plus these two things are going to be the mass 1 times gravity plus the mass 2 times gravity. We can take G out. I'm just trying to make it as simple as possible. Probably going to need a little more space here. Do that one. Okay, we have all of these things. So the power was 32,500 divided by V, which we want. This R1 400 plus 250 plus 10 G. Theta is this, so sine theta is 0.05 times 0.05, 1600 plus 800 kgs. So just substitute all these values in, and we'll get on this side, we'll get 400 plus 250 times 5 times this is 850 side, 850 this. Therefore V will be 32,500, 17.6 rounded to 1dp. The answer is 17.6. Okay, so you can see it's pretty similar to the energy ones, the work energy and the inclined slope ones, but we just have this introduction of the concept of power, which can help us make calculations for forces like the driving force. There's no really anything extra other than, I guess this is extra, that, the sum of all the forces of the system will equal 0 if the system isn't accelerating, right? The resultant acceleration will be 0 if it's moving at a constant velocity. Okay, let's do one more. A car of mass 16, okay, so you're going to see, like when you do the works, you're going to see they're all very, very similar. It's asked every year, it's like 3 marks, man. Car of mass 1600 kgs travels at constant speed. Okay, so we've got this mass of a car. So I did one where there's a connected masses. Now I'm doing one where it's just an individual mass on its own. It'll be useful because that's the only 2 real scenarios that ever comes up. Okay, this is theta. Speed So it travels at a constant speed of 20 meters per second. Its mass is 1600 kilograms. And its theta is inverse of 0.12, right? So that means that sine theta is 0.12. Okay, find the change in potential energy of the car in 30 seconds. Okay, it's moving at a constant speed for 30 seconds. Well, it's going to travel a distance because we want the change in potential energy, change in G. It's going to be mg change in H for this thing. When 30 seconds, let's say it's here. Well, it's going to move a distance d. This distance d, velocity equals distance over time, or distance equals velocity times time. So it's constant velocity for t equals 30 seconds. The distance will be 30 seconds. We get velocity is 20 times 30. The distances traveled will be what? Is that 600? Yeah, 600. Okay, so therefore we can find the change in height, which will be this. Change in height of this object as it moves this distance d. So the change sine, this is theta, right? Sine theta equals opposite, which is change in h over d. Therefore, change in height equals d sine theta. So this equals to mg d. This is d sine theta. Sine theta. Okay, and we have all these values, so it's going to equal to the mass, which was 1600, times gravity times 600, and then sine theta is 0.12. Therefore, change in G, gravitational potential. This. $1 million. It's a big number. 1,152. That's a big ass change in gravitational potential. Given that the total work done by the energy of the car in this time is this, find the constant force. Okay, so remember that we have resistance force, we have this driving force produced by the engine, and we also have this weight, Fg. B. Okay, so given that the work done, so we're given that the work done by the engine is this. So work done by this driving force is 19,600,000 joules. Right? So we can use our work energy equation. Change in kinetic energy equals the sum, right? Because we're trying to find the resisting force, which can be found through finding the work done of the resistance force. Now, because it's moving at a constant velocity, well, the change in kinetic energy will be 0, right? It's not changing velocity, so it's not changing kinetic energy. So this will be 0, so therefore we get this whole thing equals 0, yeah. So what is the sum of all the work done? So we have the work done by the driving force, which we're given, work done by the driving force, minus the work done by the resistance force, which we want to find, minus the work done by the force acting down the slope. The work done, gravity acting down the slope. Well, we have this minus this will be, this thing is FRD, right? Work done is force times distance or displacement, minus this will be FR sine theta times D. Right? I don't want to keep having to do this. Like, I've been through this in my forces, so make sure you watch them. That's why I'm going quicker here. Right, this is the force down the slope. Equals 0. Okay, so we're looking for this value. It wants the force resisting the motion. So the constant force resisting the motion, which is this FR. And we have, well, FR, this is FG sine theta. So we have everything. Yeah. So therefore we get W. We take this over, we get FR D equals to WD minus F and G is just mg. So this would be mg sine theta times D, which is just mgd sine theta. This change in G, and I went through this concept in my work energy video. This is the change in G, right? Mg sine theta, work done by the gravitational force. Mg sine theta, which we have here, so we can just use that. We don't have to calculate it. Therefore, we get FRD equals the work done. It's the change in G. So therefore, FR equals to the work driving force minus the gravitational change in gravitational energy divided by D. That equals to 1960,000 minus 1152,000 divided by 600 meters. Okay, so this will equal to 60,000 minus answer is equal to 1346.67 newtons. Around that. Yeah, 3. See, calculate in kilowatts the power developed by the engine of the car. Okay. Power equals the driving force times the velocity. Velocity is staying constant, so it's 20 meters per second. And driving force, well, how do we find the driving force? Well, the driving force, we can find it in many ways. We could solve the force, we could sum up all the forces here. Or you could, you could do it this way. You could say, the sum of all the forces is equals to 0 because it's going to be a constant velocity. Fd minus Fr minus Fg sine theta equals 0. Therefore, Fd equals to Fr minus plus Mg theta. Right. We have Fr 1346.67 plus 1600 times 10 times 0.012. 0.1. Plus 1600 times 32,000, 3,006.67 newtons. So therefore the power will equal to this. Times the velocity, which is 20. Watts. So in kilowatts, this will be 65.3 kilowatts. Just to note, another way to figure out this driving force here, right? Because we need the driving force to find the power by the engine. But another way you could do that, that because work done is by this force is FDS, right? Distance, FD times the distance. Well, that means that if we do FD, is the work done divided by the distance travels in that. So the work done, which we had, right, is this divided by 600, basically. This 1960,000 divided by 600. That gives us the same value here. There's another way you could have figured it out. Right? Get the work done. That's definitely an easier way, but I just want to show you, you know, you can figure it out through the forces as well. This is just like crucial, man. It's Newton's second law, and the work energy equation is just crucial for every single question. You understand those two equations, which I've been through, and you're good for everything practically in this exam. Calculate in kilowatts. Yeah, we did that. D. Given the power suddenly decreased by 50%, find the instantaneous deacceleration to the car. Okay, D. So we have a decrease in the power. So the power is this. We have a decrease. So the power decreases. Let's say the new power decreases by 15%. So we multiply this thing, 0.85, right? That'll decrease it by 15%. Let's multiply by this P here. By 6.5. Make sure you keep it not rounded till you get to the end. Times 0.85. New power is 277. 6.67. 2776.67 watts. So it wants, so given the power suddenly, so the engine suddenly decreases in power by 15%. So when it decreases in power, there's now instantaneous deacceleration of the car. So how do we find that? Well, we need to find, so we have the engine in the car, it's moving, this car is moving at a speed of what, 20 meters per second, right? Now it's decreasing instantly. So that means that the driving force is decreasing as well instantly. So let's find that new driving force. The new driving force here will just equal to the power over the velocity. Right, this is our new power. Right? It'll be this divided by 20. So the new driving force is this divided by 20. Oh, sorry, that'd be E times V, right? Our new power will be, the power equals FD over V. So the new hold up. Everybody hold up. Something wrong. 0.85 times 6533. I get this wrong. This. Sorry about that. Okay, look. Scratch everything I said. Look, okay. Okay, this is our new power, right? We've got a decrease in power by this. Yeah. Times that. We get a decrease in power by 15%. Not bad. That is 55,583.33 watts. And we ain't editing this shit out. You know I'm not gonna. You know, I'm not trying to be squeaky clean here. This is raw, baby. Okay, so that's it. And okay, so that's our new power. So we need our new driving force, which will simply be this divided by 20 meters per second. So our new because power equals the driving force multiplied by the velocity. So therefore the new driving force. So we have a decrease in power. So that means we have a decrease in the driving force instantaneously, but it's still moving at 20 meters per second, right? So equal to the power over the velocity, which is going to equal to this. Too many numbers here, man. Divided by 20. This gives us a new driving force of 2776.67 newtons. Okay, so this is our new driving force. What does it even want? Gone so lost it. Okay, what's the decrease in acceleration? Okay, so we know that the sum of all of the forces for this car or this system is going to equal to the mass of this car times the acceleration. In this case, deacceleration. Also, this is just FD minus, we look at the system, we got FD minus FR. We've done this before in the previous question. D minus FR, but it's not 0 anymore, right? This time it's accelerating because we've got to decrease the power. So FD minus FR minus FG sine theta. FD minus FR minus FG sine theta equals mass times acceleration. Okay, this is mg. We have this. We have this. Right? There's no change in the resistance. We have a constant force resisting the motion. And so then we can find the acceleration. So the acceleration is going to equal this. FD we have minus FR we have minus mg. We have m, we have g, we have sine theta divided by the mass. So equals to FD. It's this, the new driving force, which is 277.667 minus FR, which is 1350, but keep it in exact form, so 1346. 1346.67 minus the mass, which is 1600 times 10, gravity times 0.12. All divided by the mass, which is 16. Okay, so minus 277.667 minus 346.67 minus 1600 times 10 divided by 16. 0.3 minus, so it's in minus, which makes sense, right? Because it's deaccelerating meters per second squared. So the acceleration is this, the immediate deacceleration, I guess you could say. Immediate deacceleration to this reduction in power is 0.306 meters squared. Okay, so that's two really good questions there. Sorry for the bit of the shambles at the end there. Maybe I should take a break from doing math for a bit. For a minute, you know. I've been doing a lot recently. This stuff can be draining. Anyway, so that's it. So make sure you download that. Answered like heaps of these. Answered all of the 20, so all of the recent ones basically. And they're very similar. So just make sure, and this question will be easy if you go in like without my other videos, having watched it up to this point. You know, I've got like 7 videos before this, and obviously this is going to be difficult for you. But if you go in from the start of the playlist to here, this will be very easy for you because I've deliberately organized the playlist in a way which, when we develop to these somewhat harder questions, they're quite easy. So yeah, so just do that, and then all you're really doing is adding power into what you already know, which is a hell of a lot at this point if you've been through. Anyway, that's it. And now I'm going to really do a good discussion about energy. You know, let's talk about energy, like for real. I got the power. Energy. Everything that you see, everything that you observe has energy. There's an essence, a driving force behind everything. We disagree sometimes. I mean, honestly, all the time we've disagreed on what this energy is, and it makes sense because it's so encompassing. It's such a huge idea. We're questioning what is life? What is this force that's producing all of this? And so, you know, some people call it God, other people call it consciousness, scientists call it energy, whatever. Like, I believe that we're all trying to get at truth. Yeah, we're talking about the same thing, and it makes sense as there's larger disagreements on this thing. But it's true. Like we're trying to get at truth, energy, essence. There's a life behind things. Even the most mundane of object has massive amounts of energy. It's a completely just baffling thing And this force, man, it gives rise to all of this, everything that you can possibly experience. And it's magical, you know, it's remarkable, it's beautiful. And if it's not beautiful to you, you just need to elevate your perspective. Really just get into a higher perspective of life, and really start to see what is this shit, and how beautiful it is, and how remarkable it is, and how mysterious it is. And if you can't see it like that, just elevate your perspective, and I guarantee it will become just so incredible to you. That's one of the things that science and math and religion and philosophy and everything, psychology, all of it, we're just trying to figure this out, trying to understand it for its own sake. Understanding something for its own sake, because it's just so mysterious. It's so incredible. Keep using the same words, but I ain't got any other words for them, man. And so energy, you know, it's the driving force behind life in the scientific perspective. And so it's something we want to look at, we want to understand, because it produces everything that we can see in the physical universe. I mean, so what a topic to be learning. What a topic to be introduced to. It's not just a set of equations. This has produced your entire existence. And I feel grateful to even have the opportunity to be alive and to experience it, and to even learn a tiny slither of it. If you found this video useful, helpful, not helpful, useless, don't like, subscribe, don't subscribe. Doesn't really matter, right? Peace and love, baby.